Minus or not? Don't have my mix speaking today. Like that. I don't know correctly. Because that's eventually what we call an arm scale.
It's like a felt too. Well, good morning. I guess we get started. What we started doing last lecture was quote-unquote review of transmission line analysis. And basically what we discussed was that the proper thing to do is do a field analysis. Do Maxwell's equations for the field region and apply the boundary conditions and solve and get the proper solution. But this is kind of involved, and we'll do that when we get to waveguides. transmission line analysis using the field theory requires having that background of analyzing the waveguide. Believe it or not, it's the other way around. So, to get them in the mood of what the analysis is about and what kind of things that we will be encountering, we use circuit theory. So we take the transmission line, right, two conductors, develop a physical model, which is an approximation, because after all, when you take a field problem and reduce it to a circuit problem, you are doing an approximation. You are doing some sort of a modeling, and there's no perfect model. There's always some form of an approximation. So we say we can see a resistance in the center conductor, we can see a resistance in the outer conductor, or if to a parallel wires, whatever the conductor's shape are, there's some internal resistance. So that's our resistance per unit length, R. We use in the notation R sub Z in the chapter that you have on Scholar. Hope you all have had access to that and you can download it and work through it. I'm going to use in the lecture here R, just for the sake of reducing the complexity of the display on the board. We recognize some inductance, some inductive behavior. You've got yourself magnetic field, so there's some inductive behavior. There is some electric field, so there's capacitive behavior. And there's a dielectric that is never perfect, so there's always a leakage through that conductor, the conductance of the dielectric, and we call that the conductance. So I have RLCG. These are the simple approximation to the behavior of the transmission line, and we can actually use them to develop the first order solution to the transmission line problem. So we, recognizing that this is a distributed situation, in other words, your resistance is per unit length, your inductance, your capacitance, your inductance, and you can never write a terminal equation right away because things are distributed. So what we did is we took a small increment and we wrote the voltage at a certain location in terms of voltage at a location that's close to it, adjacent to it, a distance delta Z away from it. Right? So we wrote the two voltages in terms of each other and in terms also of the current rule. So called as V of Z plus delta Z, I of Z plus delta Z. We wrote the KBL and KCL, which are again developed from field theory. Right? So everything we are doing here is realizing that we've done kind of a loop around. We start with field theory, we develop all these tools, and now we're using the tools to solve a field problem, right? So it's just the best we can do at this point. Later on, we'll develop some muscles and we'll tackle the bigger field problem and we'll see the full field analysis and what it develops. And again, when we see it so complicated, we'll escape that to using the scattering parameters. We'll go back to the circuit theory. Well, engineers don't like too much math, right? Anyone here likes math? Right. We send this out. Well, if you love math, then you're in the right place because that's where you can use it too. It's not going to use it. You're in the wrong place. Go back to the math department. Right. Anyway, we get back to our discussion. So we developed this incremental relationship between the voltage and the current at some location versus the other. Okay? And basically, that equation is going to be a differential equation because we're writing V of Z plus delta Z in terms of V of Z. I of Z plus delta Z in terms of I of Z. When we reduce it all together, we end up with a second order differential equation like this one. All right? And this is the resistance per unit length, inductance per unit length, conductance per unit length, capacitance per unit length, the voltage derivative with respect to position in terms of the voltage itself. There was another one similar with respect to the current. We solve this equation together, and guess what? We end up with a solution of this form. V of z is equal to v plus e to the minus gamma z plus v minus e to the plus gamma z. And gamma was the square root of this quantity here, and we have two roots, and that's why we have minus and plus here. Okay? Now, why did we associate the v plus with the minus and the v minus with the plus? The v plus and v minus are simply arbitrary constants. We could have called them anything else. The reason we call them v plus and v minus will be apparent later on as we continue our discussion. And again, the equation, the current, reduces to a form like that. And like I said, chapter 2 that you have on Scholar has the full details of how we came to here and what's in between. Right? Read it carefully, and if you find anything that you don't like, please let me know. Like I told you, that's a draft for a book that I'm writing for undergraduate fields. So I appreciate if you catch any mistakes or any presentation that is not very clear, or if you think of something else that can be added also, I appreciate that. Any feedback is good. So the current I of z is going to be of the form of 1 over something times this minus that. Now, the minus sign here came from the development. It did not come from our own imagination or our own logical thinking, because sometimes people think, oh, it's minus because. No, it's minus because the mathematics proved it that way. We can explain why physically the minus sign is, but that will come in our discussion. We call this quantity here gamma squared. We call this quantity here Z naught. So we're getting rid of RLCG in our discussion now. You won't see them again in the discussion. And we're replacing them with gamma and Z naught. All right? RLCG are real numbers that are physical parameters of the transmission line. And we are translating them to two complex quantities, gamma and Z naught, that will have some physical implications as well. And we'll see in a minute. Now, gamma and Z naught are complex, as you can see. Forgot to remind you also that this is the harmonic analysis. This is assuming a harmonic source, only one frequency, right? In the discussion last time, we showed two parallel paths, one for time domain and one for frequency domain. The time domain one would have given you the opportunity to discuss multiple frequencies, right? Time domain is transient. You can have anything you want, right? Any shape or waveform. But this particular one here is only talking about one single harmonic frequency. Obviously, if you want to do harmonic analysis, you assume that you only have one frequency. You assume that you don't have any nonlinearity, because that introduces harmonics or even subharmonics. All sorts of assumptions go into this to simplify the analysis. So I'm assuming also that we have a homogeneous media. In other words, one location on the line is similar to another location. You are not going to have an R1 here and R2 there, or the dielectric is having different behavior from one place to another, or if the amplitude goes up, the parameters change, or if the temperature. Any of these things are out of the discussion. We're assuming the simplest case, uniform, homogeneous, control geometry. You go down the line, it's straight, it's not bent. You know, all these kind of things are in that analysis here. With these very, very simplified problem, we have these two solutions. So what we're going to do is erase the differential equation. We won't need it anymore. I just need here the gamma squared to continue to relate it to the physics. And I need the Z naught. So I'm going to erase this, make that the Z naught. I write what Z naught is. I can write gamma as a square root of, okay? Better than writing gamma squared. So I don't need this anymore. So here's my solution. And these are my two parameters, gamma and Z0. That, summarizes the development so far. Okay. Now, what is V plus, V minus, gamma, and Z0? We need to get physical meanings for those. Otherwise, we will lose feel for what we are doing. The important thing is you don't just do math. Okay? Math is a tool. It's a language of expression, but it expresses feelings. It expresses a physical situation. It expresses some phenomena. And if we lose touch with that, we can do the wrong math. Right? You can add instead of subtract, or you can multiply instead of take an exponential. Because math can just be the wrong tool in the wrong hands. Okay? So we have to get some feel for what's going on. Now, we realize that when we solve the differential equation, we end with constants. That differential equation was solving for this kind of situation. Here's our transmission line region. That's where the R is, and the L is, and the C, and the G, and all that, right? All that was in here. So the solution that we have is for this region here. But we have also boundaries here. We have a source, or a load, whatever, right? Usually we call that descending end of the source. And we have a load. And that the load could be also sending, it doesn't have to be, it's just like a street or a road or a highway, you can have things coming from both sides. But we typically call this a source and a load. The load could be in the form of a source as well, an internal impedance, and the source as well. The Thevenin's equivalent of any black box or given box is basically an internal impedance and an open circuit source. So the source and the load could be that way, and you could imagine signals traveling in both directions. So eventually we'll see that these are actually the two types of signals that travel in both directions. We'll see that this one here is actually a wave traveling in the positive Z direction. So this wave here is eventually be a wave traveling in this direction, and that's going to be the wave this way. And this one here will be sending a wave this way, and that's the wave coming from the load direction. And that's why the plus label here, as we'll see in a minute, and the minus label there. So the plus and minus labels are indicating the direction of propagation, and we'll see that the minus sign in the exponent indicates a positive Z propagation, and the plus sign in the exponent indicates a negative Z propagation. Right? Now, the V plus and V minus are basically the intensity of these waves. And the intensity of these waves is going to be determined by what's happening here. If you have no source and load, and you have this line laying around on your table, like in this case here, any of these cables laying on the table there, and there's no source or load, obviously those are zeros, right? Nothing is moving. If I put a source, that means I'm initiating this one here. If there's a signal coming the back way, that means I'm initiating that. So how can we determine these arbitrary constants? By applying the boundary conditions. Boundary condition 1 and boundary condition 2 are the boundary conditions that will determine the V plus and the V minus. They're going to be determined by these boundary conditions. Intensity of these waves. How many cars coming this way, how many cars going the other way, is determined by what's happening on the side of the highway and what's happening on the other side of the highway. And if there are cars that are coming back because they didn't see or they saw something that they didn't like, that all is possible. So these are the V plus and V minus. These are complex numbers. All this is phasors. So all these are complex quantities. That means magnitude and phase, right? for each one of those, real and imaginary or magnitude phase. Now, let's assume that somehow we have a source that's sending signals to simplify the situation, just one side. And this goes indefinitely. All right? That means our solution for this simple case is logically that one, right? Logically that one. Is a solution for a one-sided propagation. And we'll use that to get the physics. You know, when this picture is convoluted, you know, you don't, try to struggle too much with it. We don't want to hit our head against a concrete wall, right? We'll take a few easy steps. So let's just take a simple case of that nature, right? So we look at this one here alone, recognizing that gamma is complex. That means I can break that into a real and imaginary parts, and we'll use a different color for that. So we'll call this one here alpha plus j beta. And this is complex as well. We'll call this R naught plus j x naught. Right? We haven't reached for that one yet. Let's stick with the voltage wave. All right? So I'm going to erase the current wave because I need some space underneath, but we'll get to it back when we need it. So this now is in the form of a v plus e to the minus alpha z, e to the minus j beta z. Now this one here is constant. So that constant here, along the z, is getting multiplied by a decaying factor and a phase shift factor. So if I were to look at v of z down this line, magnitude, what do I see? I see a decaying factor. V plus magnitude e to the minus alpha z. Right away, I can assign a name for this alpha, right? It's not just a real part of gamma, it now has some physical meaning, which is the attenuation coefficient. Now, what are the units of alpha? If I go back here, that was ohms per meter, Siemens per meter, Siemens per meter. Ohms and Siemens cancel each other, and we have meter per meter per meter, and the square root is per meter. So this actually, the units here are meter to the minus 1. That's all what's left from my units. So alpha's units are again meter to the minus 1. But we have something that we add to that shows some insight into what it is, because meter to the minus 1 is many things. Alpha is meter to the minus 1, and beta is also meter to the minus 1. So the similarity in the units, right, may confuse us and may make us lose the insight or the meaning or the physical insight of that. But we know that's an attenuation. And attenuation is usually expressed in decibels, right? Because it's a unit that we use in many other forms of attenuation or gain, if you wish, when we have voltage that steps up or voltage that steps down, or power that steps up, power that steps down. We usually take the
natural log of this, all right? And you end up with gamma z, which is the gain itself. So this one here, or the alpha, where is it? Right here. This one here is now the decibels per meter, or the Neppers per meter. Now, if this is an exponent of E, the exponent here is E, then we use the Neppers. If the power that we use is or the 10 or the logarithmic of 10, the base is 10, is a decimal. The decimal is more common unit in the commercial world than the Nepper, right? But if you are given the numbers in decibels, you have to convert it to Nepper to put it in that exponent, because we use the exponent of E, we are not using 10. We are not using the exponent of 10. So this one here is Neppers per meter. Neppers meter minus 1. So the Neppers is the unit for the attenuation, and per meter becomes Nepper meter to the minus 1. And you can easily convert Neppers to meters, the conversion between natural log to the log to the base 10. All right? So that is our alpha, the attenuation coefficient. The beta, as you can see now, is a phase coefficient. So this one here will call attenuation coefficient. Neppers per meter. And this one here is a phase constant. And it is radians per meter. It's radians per meter. Now, we are trying to get some physical meaning while maintaining ourselves in the frequency domain. Believe it or not, sometimes we can do that, but we can't get really a full appreciation to things in the frequency domain. You need to get back to the time domain to have that full appreciation to things. And to do that, what we're going to do is take this back to the time domain. I'm going to take it back in the space here up. So V of Z and T, how do we do that? Anyone remembers how we get back to the time domain?
Take the real part of that thing and e to the j omega t.
You multiply first by e to the j omega t, and then you take the real part, okay? So you multiply by e to the j omega t, and take the real part. Okay? So obviously that becomes what? Becomes, this is going to be a V plus magnitude, if you wish. And you take the phase of that as e to the j phi plus, and you have the real part is going to be e to the minus alpha z. And then you have cosine omega t minus beta z. Need some space. I'm going to use this one here. I'm doing several steps in one here, plus phi sub z, phi plus. Phi plus is the phase of the V plus. So the phase of the V plus omega t minus beta z. Okay? So that's the real part. That's our solution of the voltage waveform in the time domain. Can we see that on the z-axis? Let's plot it. Now this is z. Now we have parametric situation now. This is V of z and t. V plus. V plus, I'm sorry. Remember V plus. And that's in the case of only one wave traveling, right? We eliminated the other end for now. We took it all the way to infinity, that it will never happen in our lifetime, okay? It keeps on going indefinitely. So the v plus of z and t is equal to, again, a v plus magnitude, e to the minus times cosine. So there's still an envelope. This represents an envelope here to the cosine variations here. So here's the envelope. And since the cosine will go plus and minus, it means the envelope will be up and down. This is v plus e to the minus alpha z. And this one is minus v plus e to the minus alpha z. And I multiply by cosine, so the cosine goes in between, but the cosine has a time factor in it. It has a z and phi plus. All right? So we start somewhere, right? And it goes like that. But that's for a given t. P plus is a constant, right? That's the phase of the V plus, that's a constant. But that varies. So this is for a given t. For another t, it will look like this, within the same envelope, right? That's a t2, and t3, and so on and so forth. Show the different t's there. If we examine this carefully, we will find out that as t increases, that phase increases. So actually, this is the direction of t increase. T increases this way. Which we say the phenomena or the phase propagates that way. If I take a